Okay, now, today we're starting into the second half of calculus. That doesn't mean you can forget about limits. That doesn't mean you can forget about derivatives. That just means we're going to start into something, and today we're laying the groundwork for something called integration. And we're going to start off integration by looking at a problem that arose or that people had that created the reason that they needed integration. Okay? And here's the question. If you look at this graph that I've got here in blue, how would you approximate the area for this curve from 0 to 2? So here's what I'm saying. Suppose that I've got a shape like this. Okay? I've got a shape that's like that. And I want to know the area of that. That's the question. What is that area in there? Something like this is a very valid question. Not just from a math perspective, but if you go, one day you are going to want to buy some land with a house on it or build a house or something like that. Guess what? Land doesn't come in nice squares always. How much area do you have there? If you go and look, I don't know if you're aware, but you can go and look at the maps of land, and they're very seldom in nice, perfect squares, yet they know how much land is in there. How do we know that? So my question to you right now is, how would you approximate, that's what I said, approximate that area in green there? Yes, we're recording. We are recording. How would you approximate that? It is, and y'all are smart enough to do this.
Well, should we take a derivative?
We don't have calculus. We don't need any calculus to approximate this. All we need is some geometry. How would you approximate the area? Any suggestions? Can you tell me a number and say, I guarantee you the area is less than this amount?
Yeah, we could find the area of a rectangle.
The area of where would you like to draw this lovely rectangle at?
Around going from 2 and then straight up, not following.
Okay, straight up, and where you want to stop at?
I want you to go to the left.
Right there?
Yeah.
Okay.
And then
All right, so she says I could draw that rectangle, and the area of that rectangle is what?
It's 2 by something.
2 by 5. How do you know that it's 5 tall?
because it's 5.
If you read 1, 2, 3, 4, 5, right here, if I put 0 in there, if I put this number in, I get 5 out. So it's 2 by 5, so the area of that rectangle is 10. So would you agree then that that green area has to be less than 10? Okay? Very good. Can you give me a better approximation only using rectangles? I'm not sure what you're saying. Do you want to come draw it up here for us? Rectangles.
Use like several.
Right.
Several rectangles is what I'm thinking. You were thinking triangle? Yeah. You could use a triangle, but I don't want to go there, okay? So I want to use rectangles. What do you think?
Spread it up like several.
So come draw some.
Well, I don't know.
Come draw some. Use a blue or a black there, please.
Right there. there, because then that you definitely know what that is.
Okay.
And then, well, the rest are harder.
They are harder, aren't they?
Try to find one with one map.
So you could like, but then you cross all that one.
Yeah. What if you did this? That's a rectangle we could find, isn't it? And then that rectangle we could find. Okay, very good.
Oh, and then you have triangles.
And then up here we could, maybe do something. I don't know what we'd want to do there. But would you agree if could we find the area of those 4 rectangles? You okay, hon?
I'm good.
All right. Could we find the area of those 4 rectangles?
Yes.
Would that answer be more or less than 10? Less than 10. Would the actual area be bigger than what we found for the black or smaller than? Bigger. Because we left out this little piece here, this little piece here. So if we found out, I don't know what it would be, but if we found that out, then we could say, okay, the area is between these two, right? All right. And this is a way of doing it. I want to take these black rectangles off though, and I want to show you what I think to be an easier way to draw the rectangles. All right, I'm going to draw this for my rectangles. I'm going to go from right here at 1 and up and over, and right here at 1 and up and over. What if I got those 2 rectangles? Okay? If I found the area of this rectangle right here, this one right here, and this one right here, that would be an approximation, wouldn't it? Would it be it'd be smaller than 10. Would the actual area be more than that or less than that? Less than that, because we're counting in a little extra here. Well, what would be the area of this first rectangle here? Can anybody tell me? 1 times 5. I'm going to write it down like this. 1 times f of 0, which is 5. Okay? I'm just writing that down so I'll know where I got the 5 from, okay? Now, what's going to be the area of this second rectangle, this one right here? It's going to be what? 1 times, how tall is this rectangle? How did I... f of 1. So it's going to be 1 times f of 1. And what happens when I put 1 into my function up here? No, that's a negative in front of x squared. 4. So now I get 5 plus 4, I get 9, right? So I know the answer is definitely less than that, right? Okay. Well, let's see. Is that the same problem? That's the same problem here. I just moved to the next slide, so we've got a new place to draw here. How could we get a better approximation, you think, than that? How could we do better than 9? We know it's less than 10. We know it's less than 9. Can we get anything, a closer approximation maybe?
Can you do something less than it?
Less than it meaning what?
You know, what it's between.
Okay, yeah. And how would you do that? And let's focus on drawing the rectangles vertically like I did here, because that's easier for us to deal with. Trust me.
Or maybe cut off the top a little bit, like stay inside of it.
What if we looked at these 2 rectangles? 1. Actually, that's not a very good line, is it? What if we did 1?
Yes, like
That rectangle. And when I put 2 in there. And this rectangle. Right? This rectangle is 1 times... Now, how did we decide to stop there? What is this number going to be up here? 4? Where did you get 4 from? It's the function value at 1, right? And what about for this rectangle over here? This one's going to be 1 times the function value at what? 2. And remember, this was our function all along, negative x squared plus 5. So if I put 2 in there, 2 squared is 4, 5 minus 4 is 1. So I get 1 times 1. So I get 4 plus 1. Here I get an area of 5.
So it has to be greater than 5 and less than 9.
It's got to be bigger than 5 and less than 9. Everybody agree with that? Good, good. I want to get a closer approximation.
That could be tricky.
That could be tricky, but you can do it. Without calculus, you can do it. How could you get a better approximation?
We can make another little rectangle up there.
Yeah, but I don't want to do that. Do we have to?
Do we have to do rectangle? Can we define?
No, we want to stay with rectangles because that makes it easier and lead directly into what we're wanting to do here. Triangles would kind of fit this one a little bit better, but let me ask you this. What if we did 4 rectangles? Okay? So I'm going to do 4 rectangles. I'm going to go right here at a half and go up, and then at 1 and go up, and then at 1 1/2 and go up, and at 2 and go up. So I've got 1, 2, 3, 4 rectangles. Should that give me a better approximation?
Yeah.
All right. So now, for this first rectangle, how am I going to find the area of that rectangle, of rectangle 1? It's going to be 0.5. Now, where is this 0.5 coming from? That's how long it is down here, right? Tell me how she figured out that was 0.5, someone. Half of 1, because we've got 4 of them, and we're going from 0 to 2, so 4 divided by 2, no, 2 divided by 4 is 1/2. So the rectangle is 0.5, and what's the function value? That's what I want to focus on. What function value are we using for that? 0.5. Okay? And if we put 0.5, let's write our function back up here. F of x equals negative x squared plus 5. Somebody with a calculator can figure out that that's 0.5 squared is...
4.7.
Yes, 4.75 here times the 0.5. And if we multiply those together, we get 2.875. So that's the area of rectangle 1. Figure out what the area of rectangle 2 is then. Well, let's write it down first. It's not?
You divide 4.75 by half. So it's 2.38.
Ah, yes. Why did I carry one there? Yeah. Okay, yes, it's 2.375, right? Somebody with a calculating device, try to verify that for me. 2.375. So rectangle 2. Now, how wide is rectangle 2? It's 0.5, right? What's the function value for rectangle 2? F of 1. It's really important that you can see that that's f of 1. Do you understand why it's f of 1? It's not 0.5. 0.5 is how wide. F of 1, because we came over here and that's the line, that's where the line intersects the graph at. So it's f of 1, and we've done that a couple of times now. We know that's 4, I think. 0.5 times 4, so we get 2 for that answer. So I've got 2.375 is one of my answers. I don't need to go to putty right now. And I've got 2. You see if you can come up with R3 and R4, and then we'll talk about what we can do from there. So you come up with R3 and R4. It's important that you can do this. I know it seems laborious right now, but you need to be able to do this. I'm going to stop here, and we will pick this up after the break. Okay, so you were going to find these two for me. So somebody tell me, what did you find for R3? It's 0.5, I know that. And the function value at what? 1.5. And that gave us a final answer of what out for that one? 1.375 times the 0.5. 1.375 after you did the 0.5. Multiply. 1.375. Okay. Everybody agree with that? All right. And then the last one is 0.5 times the function value at 2. So that's what, 0.5? Is that right? Okay. So there are our four numbers. And if we add them up, we get 2, 4.5, 6.25. Okay. 6.25. Okay? Now, I know y'all can do the math there. The most important thing for you to be able to do right now is, can you see the pattern? For example, where did the 0.5 come from? The width of it, the wideness of it, how wide it is. How can I figure out how wide it is? Because here's where we're headed now. Do we want to have to draw a picture every time we do this? It'd be, if we could just make it some kind of algorithm, something where we didn't have to draw a picture every time, it'd be a lot faster. So we need to figure out, how can we come up with that 0.5 without drawing out the picture? What numbers give us that 0.5? Well, how did we come up with that? Well, we wanted 4 rectangles, and we were going from 0 to 2. So we could get this 0.5 by doing the endpoint minus the endpoint divided by 4, right? And if you go back and look at the last two problems, when it was 2 rectangles, the width was 1, and if you do 2 minus 0 is 2, divided by 2 rectangles, you get 1. So that would work. How did we come up with this first function value here? Well, let's back up. Do you see a pattern to the function values? What's the pattern to the function values? 0.5. Does everybody see that? We started off here. We don't know how we got there yet. But how did we get to the next when we added 0.5? Why did we add 0.5? Why did we add 0.5? Was that just a random number? Because it was the x. So we added 0.5 because that's how far the width is of them. So to get to the next one, it's always 0.5 up higher. So you could get these numbers by just adding whatever the width is to it. Would you agree? Okay. How can I get this first one? That's the kicker. How did I get that first one? How do I know it was 0.5? That's where the rectangle ended here? The 2 by 4. What if this had been 1 to 3 instead, though? What if we had started... I guess here's what I'm asking, and I'm trying to generalize this a little bit. No, let's don't go there, okay? But you see the pattern to it. So we'll worry about where this 0.5 came from here in just a minute, okay? Now, same picture. I'm about to draw up here 4 other rectangles on this same picture, but I want you to figure out the areas and see how it's different from what we just did here, okay? Here's the first rectangle. Here's the second one. Here's the third one. And here's the fourth one. And so we'll have different letters. I'm going to use L. L1, L2, L3, L4. I'm not worried about the numbers I want to know what's the width on each one of these. Still 0.5 because we still got 4 of them. Okay. So what's the function value for this first one? Not the actual number. It's f of what? F of what? F of 0. Because see, instead of stopping right here, I went all the way to the top of the curve and went over. So this first one is f of 0. So, because see, I went all the way to the top on it. The second one went to where the curve intersects right there. What's that function value? That's f of 0.5. So that's following the same pattern as before. Once we got to 1, we just went up a half. So this one we expect to be f of 1, right? The third one, does it go up? Here's the number 1, and we went up and stopped at it. So it's f of 1. It's f of 1.5. So the same pattern holds true with those rectangles. The question is, how do we figure out the first one? Now, I used L and R for a reason here, okay? What we have just done is we have done something called finding the Riemann sums. And this is just a generic term that can be used with a lot of different formulas here. But basically, we broke this up into rectangles and we added them together to approximate the area. This one over here with the R's, this is called a right Riemann sum. Anybody got an idea of why it's called a right Riemann sum? We've got rectangles, so all of them are right angles. This one over here is called a left Riemann sum. Right, so well, for the left ones, we used which function value? The one that was on the left side. For the right one, we used which function value? The one on the right side. What if I said find the midpoint Riemann sum? Use the one in the middle. Okay, now we're not going there yet, okay? But that's what Riemann sums are. That's all they are. Is you break it up into rectangles and you either do the left side if it says left Riemann sums, the right side if it says right Riemann sums. Later on we'll do midpoints and some other little things there. So if we were to do this, we found out this was 6 1/4. This over here is going to be 5 and 5, 6, 7, 8, 9, 10. And 10.75. So we're going to figure out that it's between 6 and 10.75, I think. How could we get a better approximation? More rectangles. So if instead of 4 rectangles, what if we put 8 rectangles in here? Do you think we'd get a better approximation? Do you think it'd take longer to do? Yeah. It's kind of tedious, isn't it? It's not hard. It's just tedious to do more. And if we did more than 8, if we did 12, if we did 16, if we did 100, the more we do, the more accurate our estimate is. So if we could put 1,000,000 of them in here, we'd get a real close estimate to what it is. Actually, I don't think we have to have 1,000,000. I think about 100 will do it. Gets a real close estimate to what it is. So that's the basic premise of what Riemann sums are. Now, do your notes look like this next? Find the left and right Riemann sums for x squared between 0 and 4. Yes, ma'am.
Why the bigger value is called left Riemann sum, but the greater value, the smaller value is called right Riemann sum?
Okay, and that is not something that's always true. This is called the left Riemann sum because we use the left function value. See, we use this. Use the 4 function. This is the right Riemann because we use the ones on the right. 1, 2, 3, 4. So it's not bigger and smaller. It just happened that the left side is bigger and the right side is smaller here. When we go to the next problem, the left's going to be smaller and the right's going to be bigger. Okay? So, back to my question. Is this what your notes looks like next? I didn't think so. Okay, that's on the 10th slide. What does your next slide look like? Y'all have 10 slides? I don't have 10 slides. They're all the same thing, aren't they? Okay. That's just charts that I used to do the same thing. So let's slide down to slide number 10.
Mr. Ely, are you rotating on a microphone or something?
I am.
It's very weird, like all of a sudden I noticed that like
It sounds like
you're
you're
losing
like
it.
on a microphone.
But the microphone's only supposed to be recording over there.
Oh, well, it sounds like you're like.
Like we can
Oh.
hear you.
I don't know about that. The things in there that have those charts, don't worry about those. I mean, that really was just a different way of doing what we just did, and I don't particularly like it anymore. So let's do the left and right Riemann sums of this one. We're going to do the left to begin with, and then I'm going to let you do the right, okay? Now, I did not tell you how many rectangles up here. So we're going to say the rectangles are going to be 4. We're going to do 4 rectangles. Okay? Now, and to begin with, this first time, let's draw them out as well, okay? So we've got 4 rectangles. We're doing the left side to begin with. All right? So I'm going to come right here. What is it? Right about there. Slide 10, I think somebody said. 3 squared is 9. 2 squared is 4. 1 squared is 1. So now, I drew those 4 lines because that breaks it up into 4 even rectangles. Does that make sense? I drew a line because we're going from x equals 0 to x equals 4. So I've got a dot here at 0, then 1 up to where it intersects, 2 up to where it intersects, 3 up to where it intersects, and 4 up to where it intersects. Is that the picture y'all have? Yep.
How do you, never mind. I just saw it as going from the other way. Like,
Oh, you were doing this way?
yeah.
Ooh.
No.
Oh.
I was doing that way, but on the other side of the loop. Well, I was
Oh.
going this way.
Okay, now,
On this side.
okay, good. Understand what you're saying. We want to find the area between the x-axis and this.
Okay.
We're going to do that later. You're going to hate it, and we're going to do what you're talking about later when we put another curve up here. Hopefully we'll have found some shortcuts by then. So now, when we start talking about the left Riemann sum, we know we're going to have 4 of them. Wes, can you tell me what the width of each one of these is going to be? 1. Okay? And you can get that by looking at it or by saying 4 minus 0, that's these two numbers right here, divided by 4, that's this number over here, equals 1. Now, and I want you to write this down. What's the function value that we're going to use for the first rectangle? If we're using the left side, where is this
No,
f of 0? Because we want to use the left side. See, here's our rectangle from here to here, from 0 to 1. The left side is at 0. It's easier to see from 1 to 2. From 1 to 2, we want to use the left side. The left side is 1, so we're going to be using that rectangle right there. From 2 to 3, we're going to be using that rectangle right there. And from 3 to 4, we're going to be using that rectangle right there.
I don't see how we can have a rectangle down there.
From 0 to 1, that's hard to see as a rectangle, isn't it? Because what's its actual area? The function value is 0, so the area of that is 0. So yeah, we're really using... mathematicians take the liberty to say we're using a rectangle there. It's just a rectangle of area 0. It's one wide, but it doesn't have any height to it. What's our function value for our second one? 1. And what about for our third one? Our third rectangle is this one right here. It's going to be 2. And our fourth rectangle, the function value is going to be 3. Do you see your pattern with your function values there? So f of 1, if I put 1 into x squared, I get 1, and 1 times 1 is 1. 2 into x squared, I get 4, and 4 times 1 is 4. 3 into x squared is 9, and 9 times 1 is 9. So 9, 10, 14. So the area using left Riemann sums is 14. Go find the area using right Riemann sums. Bless you. I would use a different color if I were you. Bless you again. And now go and find the right Riemann sums.
But will the rectangles not be there?
All right, with the right Riemann sums, we're going to use the right endpoint. So from 0 to 1, which endpoint are we going to use?
It's still the same rectangle, we're just using a different endpoint.
That's right. But it's a different size rectangle because from 0 to 1, we're using the right endpoint. Look where the right endpoint is. See, we're using that rectangle. From 1 to 2, we're using that rectangle. From 2 to 3, we're using that rectangle. And from 3 to 4, we're using... From 0 to 1, we're going over to the right side, going over to 1, and go up to where it contacts the x-axis, and then draw a rectangle there. From 1 to 2, we go over to the 2, go up to where it intersects the curve, and then draw a rectangle there. From 2 to 3, we go over to 3 because we're the right one, and we're going to go up and over. And for the fourth one, we're going to go over to the 4, and we're going to go up all the way to the top and over. The width on all of them is still 1. Talk to me about the heights. How are the heights different this time? They're bigger. Okay. What's the function value for the first one? Function value of what number? 1. Okay. And then the next one's going to be 2. The next one's going to be 3. The next one's going to be 4.
So we have
1 times 1. And that gives us 25, 30. So we know our area is somewhere between 14 and 30. Now notice, remember Miranda asked a while ago, why was the left side an overestimate and the right side an underestimate? That's not the case now, is it? So you can't say the left side's always going to give me a small number or a big number. The left side's going to give you a number, the right side's going to give you a number. The real answer should be somewhere between those two numbers. Okay? One other thing, could we do this from 1 to 5 instead of 0 to 4? Would we get the same answer? Think carefully. If we went from 1 to 5, would we get the same answer as 0 to 4?
no,
Why not?
because the function value of 5.
Function value of 5 is way up here at 25. Could we go from negative 4 to 0? We could use any two numbers on here we wanted, couldn't we? Do we have to put 4 rectangles? We could put 2, 3, 4, 5, as many rectangles as we might want there. Okay? Do you feel like you have an understanding of what we're asking you to do? It's more tedious than it is hard. Would you agree with that? There's a lot of places to make mistakes with it, so I caution you with that. Now, I do want to show you this, and let's look at this problem. Is this your next problem? Okay. Last problem we're going to look at today. Find the area of the region bounded by the graph, f of x equals x cubed, the x-axis, and the vertical lines x equals 0 and x equals 1. And the main reason I'm showing you this is because when you read that, your brain goes haywire and says, this is nothing like what we've been doing in class. But it's the exact same thing. We just used a lot of different words to show you that, okay? This is how you expect to see problems worded as we get further into this. Find the area of the region bounded by the graph y equals x, f of x equals x cubed. That's our graph right here. Okay? The x-axis, where's the x-axis? Right here. The line's x equals 0, and the line x equals 1. So it's saying find this area in here. Okay, that's the same thing we've been doing. Now, what's different about this drawing and what I've been giving you? Only goes to 1. What else? Look at the graph that they gave you originally. How does that look different than what I've been doing? Does that rectangle drawn in there bother you?
Yes.
It's just there for looks, okay? It's really a reminder, how are you going to find these areas? You're going to break it up into rectangles. That rectangle means nothing as far as you're solving the problem. You do the same thing we've been doing, okay? So, how are we going to do this? I did not tell you in this problem how many rectangles. I'm going to tell you n equals 4. I want you to do a left Riemann sum. That's the number of rectangles, yes. And again, that's just the way you'd expect to see it written. N equals 4, find a left Riemann sum. Go. Give you the opportunity to see what you can come up with there.
Okay, but are we finding a little shaded area and not the white area?
Yes, we're looking for this shaded area right here is what we're looking for, okay? That right there. Okay, so if we're looking for 4 Riemann sums on the left, I think this is what our graph would look like. Gloria, what's going to be the width of each of these rectangles? 0.25. Because we've got 1 minus 0 divided by 4, so each of them is 0.25. All right? Now, Madeline, can you tell me what's the function, what's the x value we're going to put into the function for the first one? 0. And how do we get to the next function value, Drew? All right, what's going to be the number that we put into the function for the next rectangle? Because we're looking at this rectangle right here. How do we know what that left side is? Who can help us out there?
Well, you add 0.25 again, so it'd be 0.5.
Yeah. It's the number that we started with, 0, plus that number down there, plus the 0.25. So this becomes 0.25. The next one becomes the number you had in the previous function times the width down there, 0.5. And again, it's the number you had in the previous one times that one, 0.75. Function value at 0 is 0, so we get a 0. Oh, 0.25, 1/4 cubed is 1/64.
It's
0.004, okay. And the 0.5
0.031.
and the 0.75.
0.105.
And if we add those together, 0.140?
Yes.
Okay. We can do this? Okay. All right. We're going to talk a little bit more about this tomorrow. So before you come to class tomorrow, you need to be sure you've downloaded those notes. What I think Riemann Sum continued. You also can go ahead and probably start working on that homework assignment that's not due until Tuesday. You have a web assignment that's due, I think, on Tuesday of next week also. But it's all over just what we've been over here. So you should be able to go ahead and jump in and start working on some of that. Nothing's due this week, but if you look at next week, you've got something due Tuesday, Wednesday, Thursday, and Friday of next week. So, all right.